Welcome to Zscaler for Engineers. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this comprehensive series, we will explore the Zscaler Zero Trust Exchange platform from an engineering perspective. Whether you are a network engineer, security architect, or DevOps professional, this presentation will provide you with the technical knowledge required to understand, design, and implement Zscaler solutions in your enterprise environment. Zscaler represents a fundamental shift in how we approach network security. Traditional security models relied on a castle and moat approach where firewalls protected a defined network perimeter. This worked well when users, applications, and data resided within corporate boundaries. However, the modern enterprise is vastly different. Today, users work from anywhere using various devices. Applications have moved from on-premises data centers to multiple cloud providers. Data flows between software as a service applications, public clouds, and traditional infrastructure. The concept of a network perimeter has essentially dissolved. Zscaler addresses this new reality with a cloud-native security platform built on zero-trust principles. Instead of protecting a network, Zscaler protects individual connections between users and applications. This approach is more aligned with how modern businesses operate and provides superior security outcomes. Throughout this presentation, we will cover the Zero Trust Exchange architecture, the main product components including Zscaler Internet Access and Zscaler Private Access, deployment models, policy configuration, and operational best practices. By the end, you will have a solid foundation for working with Zscaler in real-world environments. Zero Trust Security Principles. Zero Trust is not a product but rather a security philosophy and architectural approach. The core premise is elegantly simple but profoundly different from traditional security thinking. Never trust, always verify. In a zero-trust model, no user, device, or connection is inherently trusted regardless of whether it originates from inside or outside what was traditionally considered the network perimeter. Every access request must be authenticated, authorized, and encrypted. Trust is established on a per-session basis and can be revoked at any time. The first principle is to verify identity explicitly. Every access request must prove the identity of the user through strong authentication. This typically involves integration with identity providers and may include multi-factor authentication. The identity context includes not just who the user is but also what device they are using, where they are connecting from, and what time the access is occurring. The second principle is to use least privilege access. Users should only have access to the specific applications and resources they need to perform their job functions. This is a departure from network-based access where being on the corporate network granted broad access to many resources. With zero trust, access is granted application by application based on user roles and policies. The third principle is to assume breach. Even with strong controls, organizations must operate under the assumption that adversaries may already be present in the environment. This drives several important architectural decisions. Microsegmentation prevents lateral movement. Continuous monitoring detects anomalous behavior. Encryption protects data even if it is intercepted. The diagram illustrates how these principles work together in a zero-trust flow. When a user makes a request, it must first pass through identity verification where the user and device identity are confirmed. Then policy check evaluates whether this user should have access to the requested resource based on defined policies. Risk assessment examines the context of the request including device posture and location. Only after passing all these checks is a secure connection established directly to the application, without placing the user on the LAN. Zero Trust Exchange Core Components. The Zero Trust Exchange is composed of several key components that work together to deliver comprehensive security. Understanding these components is essential for architects and engineers who will design and implement Zscaler solutions. The central authority is the brain of the Zscaler platform, It is a globally distributed, highly redundant policy engine that stores configuration, distributes policies to secure service edges, and coordinates the overall operation of the platform. When you make configuration changes in the Zscaler admin portal, those changes are pushed to the central authority and then distributed to all relevant secure service edges within seconds. This ensures consistent policy enforcement regardless of where users connect. Public service edges are the enforcement points where security policies are applied to traffic. These are Zscaler-owned and operated infrastructure deployed in data centers around the world. When users connect to Zscaler, they are automatically routed to the nearest healthy public service edge. This is where TLS inspection, threat detection, data loss prevention, and access control decisions happen. The global distribution ensures low latency for users regardless of their location. Private service edges extend the Zero Trust Exchange into customer environments. These are virtual appliances that can be deployed in an enterprise data center or cloud environment. They are useful for scenarios where traffic should not leave the local environment, such as latency-sensitive applications or regulatory requirements. Private service edges receive policies from the central authority and provide the same security capabilities as public service edges but within the customer's infrastructure. App connectors are lightweight software agents that provide connectivity to private applications. They are deployed on the same LAN segment as the applications they front. App connectors establish outbound connections to the Zscaler cloud, so there is no need to open inbound firewall ports or expose applications to the internet. When a user needs access to a private application, the Zero Trust Exchange brokers a connection through the app connector. Zscaler Client Connector is the endpoint agent that forwards traffic from user devices to the Zero Trust Exchange. It supports Windows, Mac OS, Linux, iOS, and Android. The client handles traffic steering, certificate installation for TLS inspection, and user authentication. It is the primary method for onboarding user traffic to Zscaler. Zscaler Private Access-ZPA. Zscaler Private Access, or ZPA, provides zero trust access to private applications without using VPN. This is a transformative capability that changes how organizations provide remote access to internal resources. Instead of extending the LAN to remote users, ZPA connects users directly to specific applications. The fundamental difference between ZPA and VPN is the scope of access granted. With a traditional VPN, when users connect, they are assigned an IP address on the corporate network. This gives them broad network-level access, meaning they can potentially reach any system that is raw table from their assigned subnet. With ZPA, users never join the network. They are connected only to the specific applications they are authorized to use based on policy. This application-level access model significantly reduces risk. An attacker who compromises a user's credentials cannot use that access to scan the network, perform lateral movement, or attack systems the user is not authorized to access. The attack surface is dramatically reduced compared to VPN-based access. ZPA uses an inside-out connectivity model. Application connectors deployed near private applications establish outbound tunnels to the Zscaler cloud. These tunnels are always on and maintained by the application connector. When a user needs to access an application, the Zero Trust Exchange brokers the connection through the existing tunnel. No inbound ports need to be opened, and applications remain invisible to the internet. The ZPA architecture involves several components working together. Users with Zscaler Client Connector connect to the ZPA Public Service Edge. Here, their identity is verified and policies are evaluated. If access is authorized, the service edge instructs the appropriate app connector to establish a connection from the application side. The two connections are stitched together, creating an end-to-end encrypted path between the user and the application without ever placing the user on the network. In the diagram, you can see the ZPA architecture. The user with ZCC installed makes an application request. This request goes to the ZPA service edge in the cloud. The central authority verifies identity and checks policies. The app connector, which maintains an outbound connection to the cloud, is instructed to connect to the private application. The service edge brokers the connection between user and application, creating direct secure access without network access. Traffic flow through Zero Trust Exchange. To fully understand how Zscaler protects your organization, let us walk through the complete traffic flow for both internet-bound and private application traffic. This end-to-end understanding is essential for troubleshooting and architecture decisions. When a user on a device with Zscaler Client Connector installed initiates a connection, the client first determines how to handle the traffic. Based on the forwarding profile configuration, traffic may be sent to Zscaler for inspection or allowed to go direct. The client uses techniques like DNS prefetch and app profiling to make these decisions efficiently. For internet-bound traffic handled by ZIA, the client establishes a tunnel to the nearest ZIA public service edge. This tunnel is encrypted using TLS. The traffic arrives at the service edge where the user's policies are retrieved from the central authority. The traffic is then processed through the security stack, which includes URL filtering, secure sockets layer inspection, threat protection, DLP, and firewall policies. If the traffic passes all policy checks, it is forwarded to the destination. Return traffic follows the reverse path. The destination responds to Zscaler, which performs any return traffic inspection, and then forwards the response back to the user through the established tunnel. For private application traffic handled by ZPA, the flow is different. When the user attempts to access a private application, the client contacts the ZPA service edge. The service edge verifies the user identity and evaluates access policies. If access is permitted, the service edge signals the appropriate app connector to establish a connection to the target application. The app connector creates an outbound connection to the application server. This connection, along with the user's inbound connection, is brokered together by the service edge. Data flows through these stitched tunnels, providing end-to-end encryption. Importantly, the user never receives an IP address on the application network and cannot route to any system other than the authorized application. The sequence diagram on the slide illustrates these flows. For ZIA traffic, you can see the user connecting to ZIA secure service edge, policies being retrieved, security inspection occurring, and traffic being forwarded to the internet. For ZPA traffic, the diagram shows the additional step of app connector involvement where the connection is brokered rather than proxied. Zscaler Client Connector Overview. The Zscaler Client Connector, often abbreviated as ZCC, is the lightweight agent that runs on user devices to forward traffic to the Zero Trust Exchange. It is a critical component of any Zscaler deployment and supports multiple operating systems including Windows, Mac OS, iOS, Android, and Linux. The client connector performs several important functions. First, it handles traffic forwarding by intercepting network traffic on the device and directing it to Zscaler for inspection. This can use various techniques including a local proxy, tunnel modes, or packet filtering depending on the platform and configuration. Second, the client connector handles user authentication. When a user logs in, the client authenticates them against the configured identity provider, typically through SAML. This authentication establishes the user identity that will be used for policy evaluation. The client can also perform device posture checks to ensure the device meets security requirements. Third, the client connector manages certificates for TLS inspection. For Zscaler to decrypt and inspect HTTPS traffic, it must present a certificate that the user's browser trusts. The client connector can automatically install the Zscaler root certificate, simplifying deployment. The client connector can be deployed through various methods. Enterprise MDM solutions like Microsoft Intune, Jamf, or VMware Workspace ONE can push the client to manage devices. The installer accepts command line arguments for configuration including the cloud name and user domain. For testing, Users can download and install the client manually from the Zscaler Client Connector portal. Client connector policies control the behavior of the client. These policies define settings like which traffic to forward to Zscaler, whether to allow users to disable the client, trusted network detection, and update settings. Policies are configured in the Client Connector portal and pushed to enrolled clients. The diagram shows the Client Connector architecture. The Client Connector sits on the user device and communicates with the Client Connector portal for configuration and policy updates. When the user accesses resources, the client forwards traffic to ZIA Service Edge for Internet traffic or ZPA Service Edge for private applications. The admin portal provides centralized configuration management for all connected clients. App Connector Architecture. The App Connector is a critical component of Zscaler Private Access that enables secure connectivity to private applications. Understanding its architecture and deployment requirements is essential for any engineer implementing ZPA in their environment. An app connector is a lightweight virtual machine or Linux package that runs in your data center, cloud environment, or any location where private applications reside. Its primary function is to establish outbound connections to the Zscaler cloud, creating secure tunnels through which user traffic can reach applications. This inside-out connectivity model is fundamental to ZPA's security architecture. The App Connector never accepts inbound connections from the Internet. It only initiates outbound connections to the ZPA cloud using port 443. This means you do not need to open any inbound firewall ports or expose any systems to the Internet. Applications behind app connectors remain completely invisible to external scanning and reconnaissance. When an app connector starts up, it uses a provisioning key to authenticate with the Zscaler cloud. This key is generated in the ZPA admin portal and embedded in the connector during deployment. Once authenticated, the connector establishes a persistent control channel with the ZPA central authority. This channel is used for configuration updates, health monitoring, and connection signaling. The connector also establishes data tunnels called Z-tunnels to ZPA service edges. These tunnels carry the actual application traffic. When a user requests access to an application, the service edge signals the appropriate app connector through the control channel. The connector then establishes a connection to the target application and the traffic flows through the existing tunnel infrastructure. Looking at the diagram, you can see the app connector deployed in the data center network segment alongside private applications. The connector establishes outbound connections through the firewall to the Zscaler cloud. The control channel goes to the central authority for management. The Z-tunnels connect to service edges for data transport. When a user requests access, the traffic flows through the service edge and Z-tunnel to reach the application via the app connector. App connector groups and scaling. App connector groups are organizational constructs in ZPA that control how connectors are managed and how traffic is distributed. Understanding groups is essential for building scalable, resilient ZPA deployments. A connector group is a logical collection of app connectors that share common characteristics. All connectors in a group typically serve the same set of applications and have equivalent network access. When you define applications in ZPA, you associate them with connector groups rather than individual connectors. This provides flexibility and resilience. When a user requests access to an application, ZPA selects a healthy connector from the associated group to handle the connection. The selection is based on connector health, load, and proximity. If one connector in the group is unavailable or overloaded, traffic automatically shifts to other connectors in the group. This provides inherent load balancing and failover. Scaling ZPA is achieved by adding more app connectors to groups rather than scaling up individual connector resources. Horizontal scaling is the recommended approach for several reasons. First, it eliminates single points of failure. Second, it allows rolling updates without service interruption. Third, it provides more flexibility in handling varying load patterns. Connector groups also control the software update schedule. Each group has an update window defined in the Zscaler portal. During this window, connectors in the group are updated one at a time. Zscaler's backend orchestrates the updates to ensure minimum impact. You should schedule update windows during low usage periods for your organization. For geographically distributed environments, you should create separate connector groups for each location. This ensures that user traffic is handled by connectors in the same region as the applications, minimizing latency. Users are automatically routed to the optimal connector based on their location and the application's associated connector group. The diagram illustrates a multi-site deployment architecture. The US Data Center Connector Group contains 2 app connectors that serve US applications. Similarly, the EU Data Center Connector Group has 2 connectors serving EU applications. The Zscaler Cloud routes user traffic to the appropriate group based on application configuration and user location. This design provides both high availability within each site and geographic optimization. Zscaler Access Policies. Access policies in Zscaler determine who can access which applications under what conditions. These policies are the enforcement mechanism for zero trust principles, ensuring that users only get access to the specific applications they are authorized to use. Zscaler access policies are evaluated in order from top to bottom. When a user requests access to an application, Zscaler evaluates each policy rule sequentially until it finds a match. The first matching rule determines whether access is allowed or denied. This means that rule ordering is critical, and more specific rules should generally be placed before broader rules. Each policy rule consists of several components. The rule name and description help administrators understand the rule's purpose. The conditions define when the rule applies, such as which users, groups, or device types. The applications specify which application segments or segment groups are covered by the rule. The action determines whether matching requests are allowed or blocked. Policy conditions can be based on multiple factors. User identity from your identity provider is the most common condition. You can specify individual users, groups from your directory, or SAML attributes. Device posture conditions can require that devices meet certain security requirements like having updated antivirus or disk encryption enabled. Location conditions can restrict access based on the user's geographic location or IP address. The client connector performs posture checks on the endpoint and reports device attributes to Zscaler. You can create posture profiles that define the required device state, such as operating system version, firewall enabled, or certificate presence. These profiles can then be referenced in access policies to ensure that only compliant devices can access sensitive applications. The diagram shows the policy evaluation flow. When a user submits an access request, it first goes through identity verification where user identity is confirmed via SAML. Then device posture check validates that the device meets security requirements. Application authorization checks if the user has policy allowing access to the requested application. If all checks pass, connection established creates the secure path to the application. If any check fails, access denied is returned and the user cannot reach the application. Secure Sockets Layer Inspection Configuration. Secure Sockets Layer Inspection, also called TLS inspection or HTTPS inspection, is critical for effective security because the vast majority of web traffic is now encrypted. Without secure sockets layer inspection, security tools cannot see the content of encrypted connections, creating a massive blind spot that attackers can exploit. Zscaler performs secure sockets layer inspection using a man-in-the-middle approach. When a user connects to an HTTPS site, ZIA terminates the secure sockets layer connection from the user, inspects the decrypted content, and then establishes a separate secure sockets layer connection to the destination. To make this work without browser warnings, ZIA presents a certificate signed by the Zscaler Intermediate Certificate Authority, which must be trusted by user devices. The Zscaler root certificate needs to be installed on all devices that will have their traffic inspected. This can be done manually, through Zscaler Client Connector, which can auto-install the certificate, or through enterprise certificate deployment mechanisms like group policy or MDM. Without the certificate installed, users will see certificate warnings for every HTTPS site. Not all traffic should be secure sockets layer inspected. Some applications use certificate pinning and will break if traffic is intercepted. Certain categories like healthcare and financial sites may have regulatory or privacy requirements that preclude inspection. Zscaler provides secure sockets layer inspection policies that let you bypass inspection for specific URL categories, applications, or destinations. Common bypass categories include medical, financial, and government sites. Secure sockets layer inspection policies in ZIA are evaluated before other security policies. You create rules that specify which traffic should be inspected, bypassed, or blocked. Bypass rules prevent decryption but still allow other policy enforcement based on destination. Do not inspect rules bypass both decryption and deep inspection. Understanding the interaction between secure sockets layer policies and other security policies is important for achieving desired security outcomes. The diagram shows the secure sockets layer inspection flow. The user initiates an HTTPS request which arrives at ZIA service edge. At the secure sockets layer termination step, ZIA terminates the client secure sockets layer session. Content inspection then examines the decrypted traffic for threats and policy violations. Secure sockets layer re-encryption establishes a new encrypted connection to the destination server. Response traffic follows the reverse path. Throughout this process, the user maintains a secure connection to ZIA, and ZIA maintains a separate secure connection to the destination. Data loss prevention (DLP). Data loss prevention in Zscaler protects sensitive information from leaving your organization through web and cloud channels. DLP policies detect and block the transmission of confidential data like credit card numbers, social security numbers, intellectual property, and other sensitive content. Zscaler DLP operates inline, inspecting traffic in real time as it passes through the Zero Trust Exchange. When users upload files, post content to websites, or send data to cloud applications, DLP engines analyze the content looking for sensitive patterns. If a policy violation is detected, the transaction can be blocked, quarantined for read review, or allowed with logging. DLP detection uses multiple techniques. Pattern matching identifies structured data like credit card numbers, social security numbers, and phone numbers using regular expressions and algorithms that validate the data format. Dictionary matching looks for keywords and phrases that indicate sensitive content, such as confidential, proprietary, or specific project code names. Exact data match, or EDM, is an advanced technique that fingerprints actual sensitive records from your databases. You can upload hashed versions of customer records, employee data, or other sensitive datasets. When DLP sees data that matches these fingerprints, it can take action. EDM is highly accurate because it matches against your actual data rather than general patterns. Indexed document match, or IDM, fingerprints entire documents rather than individual records. This is useful for protecting forms, contracts, or other templated documents that contain sensitive information. When a document matching a fingerprinted template is detected, DLP can block its transmission. Optical character recognition extends DLP to images and scanned documents. The diagram illustrates the data loss prevention inspection flow. When a user initiates a data upload, it goes to ZIA service edge. Content extraction pulls the data from the transaction. Pattern matching looks for structured sensitive data. Dictionary matching checks for sensitive keywords. EDM and IDM matching compares against fingerprinted data and documents. If policy evaluation determines a violation, the data is blocked. If no violation is found, the upload is allowed to proceed to the destination. Cloud Access Security Broker (CASB). The Cloud Access Security Broker, or CASB, capabilities in Zscaler provide visibility and control over software as a service applications. As organizations adopt more cloud services, CASB becomes essential for understanding what applications are in use and ensuring data is handled appropriately. Zscaler CASB operates in two modes. Inline CASB, also called forward proxy mode, inspects traffic in real time as users access cloud applications. This mode can enforce real-time policies like blocking file uploads to personal cloud storage. Out-of-band CASB, also called API mode, connects directly to software as a service applications via their APIs to scan data at rest and monitor sharing settings. Shadow IT discovery is a key CASB function. ZIA analyzes web traffic to identify all cloud applications being used in your organization, including ones that IT has not sanctioned. The discovery dashboard shows you which applications are in use, how many users access them, and the risk level of each application. This visibility helps you make informed decisions about which applications to sanction, monitor, or block. For sanctioned applications, CASB provides granular controls. You can create policies that differentiate between corporate and personal instances of the same application. For example, you might allow users to access corporate OneDrive but block personal OneDrive accounts. Tenant restrictions ensure that users can only access your organization's cloud instances, preventing data exfiltration to personal accounts. Out-of-band CASB scanning connects to software as a service applications like Office 365, Box, Google Workspace, and Salesforce through APIs. It scans files stored in these applications looking for sensitive data, malware, and compliance violations. It also monitors sharing settings to identify files that are inappropriately shared externally. Remediation actions can automatically revoke risky sharing or quarantine suspicious files. The diagram shows the CASB architecture. Users access software as a service applications through inline inspection at ZIA Service Edge where real-time policies are enforced. API scanning provides out-of-band access to scan data at rest in the software as a service applications. Shadow IT discovery analyzes traffic patterns to identify all cloud applications in use. The CASB dashboard provides visibility and control, feeding into DLP integration for data protection and policy enforcement for access control. This comprehensive approach covers both real-time and at-rest data protection for cloud applications. Zscaler Digital Experience (ZDX) Overview. Zscaler Digital Experience, commonly known as ZDX, is a digital experience monitoring solution that provides end-to-end visibility into user experience across applications, networks, and devices. In today's distributed work environment, understanding and optimizing the digital experience has become critical for maintaining productivity. Traditional monitoring tools were designed for an era when applications lived in data centers and users worked from offices. They relied on instrumenting the network and applications at fixed points. With users now working from anywhere and applications distributed across multiple clouds, these traditional approaches create significant blind spots. ZDX takes a different approach by monitoring from the user's perspective. It leverages the Zscaler client connector that is already deployed on user devices to continuously probe application performance and collect device telemetry. This means there is no additional agent to deploy if you already have client connector installed for ZIA or ZPA. The platform generates a ZDX score for each user, application, and location. This score is a composite metric that reflects the overall digital experience quality. When scores drop, ZDX provides drill-down capabilities to identify whether the issue is in the user's device, their local network, their ISP, the Zscaler cloud, or the application itself. This dramatically reduces mean time to resolution for experience issues. ZDX also includes AI-powered root cause analysis. When problems occur, the platform can automatically identify the most likely cause based on patterns across all monitored users and applications. This is particularly valuable for help desk teams who can quickly pinpoint issues without extensive manual troubleshooting. The diagram shows the ZDX architecture. Users with Zscaler Client Connector generate monitoring data from their devices. This data flows through the network path in Zscaler Cloud to reach applications. ZDX collects telemetry at each hop and sends it to the ZDX Analytics engine. The ZDX dashboard presents the analyzed data with ZDX scores, AI-powered root cause analysis, and alerting capabilities. This end-to-end visibility enables proactive identification and resolution of experience issues. Traffic forwarding methods. Getting user traffic to the Zscaler cloud is the first step in any deployment. Zscaler supports multiple traffic forwarding methods, each with different characteristics suited to different use cases. Understanding these options helps you design the optimal architecture for your environment. Zscaler Client Connector is the primary and most comprehensive forwarding method for end-user devices. The client runs on Windows, Mac OS, iOS, Android, and Linux. It intercepts traffic at the device level and forwards it to Zscaler through an encrypted tunnel. Client Connector supports both ZIA and ZPA traffic and provides the richest set of features including device posture checking and ZDX monitoring. PAC files, or proxy auto-configuration files, provide browser-based traffic forwarding without requiring an agent. The PAC file contains JavaScript logic that tells the browser which proxy to use for different destinations. PAC files are useful for unmanaged devices or as a fallback when Client Connector cannot be deployed. However, they only forward browser traffic and do not support ZPA or non-browser applications. GRE and IPsec tunnels forward traffic from network devices like routers and firewalls. This method is commonly used for branch office deployments where traffic from an entire site is forwarded to Zscaler. GRE tunnels are simpler to configure but do not encrypt traffic. IPsec tunnels provide encryption but require more configuration. Both methods forward all traffic from the site regardless of user identity. Cloud Connector is a virtual appliance that forwards traffic from cloud workloads. It is deployed in AWS, Azure, or GCP and configured to receive traffic from cloud resources. Cloud Connector is essential for securing east-west traffic between cloud workloads and for providing workloads with secure internet access through ZIA. The diagram compares the four forwarding methods. Client Connector on user devices provides per-user forwarding with full ZIA and ZPA support. PAC file in browsers offers browser-only forwarding without an agent. GRE or IPsec tunnel from site routers enables site-wide forwarding for branch offices. Cloud Connector in cloud VPCs handles workload traffic forwarding. All methods connect to ZIA Secure Service Edge, but only Client Connector connects to ZPA Secure Service Edge for private application access. Cloud Workload Security Architecture. Securing cloud workloads requires a different approach than securing user traffic. Workloads in AWS, Azure, and GCP need secure internet access for updates and external API calls, protection from threats, and secure connectivity to other workloads and data centers. Zscaler Cloud Connector addresses these requirements. Cloud Connector is a virtual appliance deployed within your cloud VPC or VNet. It acts as the default gateway for workload traffic, forwarding it to the Zscaler cloud for inspection. This enables all the same security controls available for user traffic, including uniform resource locator filtering, threat protection, data loss prevention, and firewall policies to be applied to workload traffic. The deployment architecture varies by cloud provider. In AWS, Cloud Connector can be deployed using Gateway Load Balancer for a distributed model or Transit Gateway for a centralized model. The Gateway Load Balancer approach places Cloud Connector endpoints in each workload VPC, providing local inspection. The Transit Gateway approach routes all traffic through a central security VPC containing Cloud Connectors. For workload-to-workload communication, ZPA can be used to provide zero trust segmentation. Just as ZPA connects users to applications, it can connect workloads to other workloads. This prevents lateral movement in the cloud environment. A compromised workload cannot scan or attack other workloads because there is no network-level connectivity between them. Cloud Connector also enables secure connectivity between cloud and on-premises environments. Traffic from cloud workloads destined for the data center can be forwarded through Zscaler and out through app connectors, providing consistent security inspection for all traffic regardless of direction. The diagram illustrates cloud workload security architecture. The Cloud VPC contains workloads that route traffic through Cloud Connector. Cloud Connector forwards traffic to ZIA Service Edge for security inspection. For Internet-bound traffic, the path continues from ZIA to the Internet. For accessing private resources in the data center, traffic goes from ZIA through ZPA Service Edge to the App Connector, which connects to private applications. This architecture provides comprehensive security for all workload communication paths. Troubleshooting ZIA issues. Effective troubleshooting is a critical skill for any engineer managing Zscaler deployments. ZIA issues typically manifest as blocked access, slow performance, or authentication problems. A systematic approach helps identify root causes quickly. When users report that websites are blocked unexpectedly, start by checking the ZIA transaction logs. The logs show every request processed by ZIA, including the URL, user, policy matched, and action taken. If traffic is being blocked, the logs will show which policy rule triggered the block. You can then evaluate whether that rule should apply or needs adjustment. For performance issues, examine whether Secure Sockets Layer inspection is contributing to latency. SSL inspection adds processing overhead, and some sites may perform better when bypassed. Check if the slow sites are in categories that should be bypassed. Also verify that users are connecting to the nearest Zscaler data center by checking their client connector status and comparing with the geographic data center locations. Authentication issues often stem from identity provider configuration problems. If users cannot authenticate, verify that the secure SAML configuration is correct in both Zscaler and the identity provider. Check that the assertion consumer service URL matches exactly. Review the identity provider logs to read if assertions are being generated successfully. Common issues include clock skew, certificate mismatches, and incorrect attribute mappings. Client connector problems can prevent traffic from reaching Zscaler at all. The client connector logs on the device provide detailed information about connection status, authentication state, and any errors. Look for tunnel establishment failures, certificate issues, or network connectivity problems. The client connector also has a built-in diagnostic mode that can help identify issues. The troubleshooting workflow diagram shows the systematic approach. Start at user reports issue. First, check client connector status to verify the client is connected. Then verify authentication to ensure the user session is valid. Next, review transaction logs to see how requests are being processed. Identify policy match to determine which rule is affecting traffic. Based on findings, either adjust policy if the rule is incorrect or resolve other issues such as network or application problems. This methodical approach ensures efficient problem resolution. Logging and reporting. Comprehensive logging and reporting are essential for security operations, compliance, and troubleshooting. Zscaler provides extensive logging capabilities that capture detailed information about every transaction processed by the platform. ZIA logs include web transaction logs showing every HTTP and HTTPS request, firewall logs for non-web traffic, DNS logs, and sandbox analysis logs. Each log entry includes timestamp, user identity, source and destination information, policy matched, action taken, and thread details if applicable. These logs can be searched and filtered in the admin portal for quick analysis. ZPA logs capture authentication events, application access requests, and connector activity. The logs show which users accessed which applications, when, and from where. Policy evaluation details are included, showing why access was granted or denied. Connector logs track tunnel health and connection brokering activity. For long-term storage and analysis, Zscaler provides Nanolog Streaming Service, or NSS. NSS streams logs in real time to your SIEM or log management platform. Supported destinations include Splunk, QRadar, ArcSight, and cloud platforms like Azure Sentinel and AWS Security Lake. NSS enables you to correlate Zscaler data with other security telemetry for comprehensive threat detection. Built-in reports provide insight into security posture, user activity, and policy effectiveness. Standard reports cover topics like top blocked threats, bandwidth usage by application, and cloud application discovery. You can schedule reports for regular delivery to stakeholders. Custom dashboards allow you to create visualizations tailored to your specific monitoring needs. The logging architecture diagram shows the data flow. ZI as Service Edge and ZP as Service Edge generate transaction logs and access logs respectively. These flow to the Zscaler cloud where they are stored in the log database. From there, logs can be accessed through the admin portal for interactive analysis, streamed via NSS to SIEM platforms like Splunk or QRadar, or used to generate reports delivered via scheduled delivery. This flexible architecture supports both real-time and historical analysis needs. Best practices and summary. As we conclude this presentation on Zscaler for engineers, let us review the key best practices that will help ensure successful deployments and ongoing operations. For deployment planning, start with a clear understanding of your use cases. Identify which users need ZIA for internet security, which need ZPA for private application access, and which need both. Map out your application inventory and determine which applications will be accessed through ZPA. Plan your connector deployment to provide adequate capacity and redundancy. Always deploy app connectors in pairs for high availability. Size connector groups based on expected user load, allowing for approximately 500 concurrent users per connector. Position connectors on the same network segment as the applications they serve to minimize latency. Establish a regular schedule for reviewing connector health and performing maintenance. Implement secure sockets layer inspection broadly but with appropriate exceptions. The vast majority of traffic should be inspected to maintain visibility into threats. However, maintain bypass lists for certificate-pinned applications and regulated content categories. Test new applications before enabling inspection to identify any compatibility issues. Use the principle of least privilege in your access policies. Start with deny all and explicitly grant access only to required applications. Regularly audit policy configurations to remove stale rules and verify that access grants are still appropriate. Leverage device posture checks to ensure that only compliant devices can access sensitive applications. Integrate Zscaler logging with your SIEM for comprehensive security monitoring. Establish alerting rules for critical events like blocked malware, DLP violations, and authentication failures. Use ZDX proactively to identify and resolve experience issues before they impact user productivity. Thank you for your attendance. Please consider subscribing to the channel and liking this video.